Markov models. Now, if we go back to the lecture that I had on randomness and prediction for details, so this is lecture 3 in week 3. And remember, I posed the following question: how many seconds into the future can we predict a football match? And we talked about this. Maybe we can predict 1 minute, 10 seconds, 1 second. Now that's really important because we agreed that we can't really predict 1 minute, certainly can't predict 90 minutes into the future of a football match. We can't really predict 45 minutes or even 15 minutes. And I think it's doubtful that we can even predict 1 minute into the future of a football match, more than we could have predicted at the start of the match, maybe to some sort of very small level, but not very reliably. But maybe we can start to predict 10 seconds or certainly 1 second into the future. If a player is about to shoot, then we can predict that there's a higher chance that it's going to be a goal. So somewhere around 10 seconds is how much that we can predict the future of a football match. And that turns out to be a very useful property. Oh, somebody's got their microphone on. Sorry. I hadn't muted all the participants. That turns out to be a very useful property for building models about evaluating players. And the first model of this type, which I write about in the pro version of Soccermatics, was proposed by Sarah Rudd, and you can still find the details of her talk online. And this is now, well, it's almost 10 years old. It's certainly 10 years old when she developed it. And her idea was that to use this memoryless property of football to evaluate the chance of scoring from different positions. And the first thing you have to do in doing this is you look at, if you've got the ball here in midfield, for example, what's the probability, maybe 5 seconds into the future? You have to choose a time scale. What's the probability 5 seconds into the future it's on the wing? What's the probability 5 seconds into the future it's in the box? What's the probability 5 seconds of the future it's in the goal that there's been a shot? Or what's the probability if we lost it? And what's the probability it's still in midfield? And you can work out these probabilities just by observing all the times you've got the ball in midfield and finding out how often the ball goes into these different areas. And that gives you a start for what we would call a Markov chain model of football, because once the ball has gone out to the wing, if this is the next thing has happened, we forget the fact it was in the midfield and we start to work out what's the probability it goes from the wing into the box, what's the probability when it goes into the goal, and so on. And that way, we build up a model of the sequence of things that can happen in football based on the memoryless assumption. I'll just go into a little bit more detail about what she did. Again, you can watch her talk online, and the slides are available here. The story is for Sarah Rudd, which is quite cool, is that she gave this talk and then she was picked up by Arsenal and they signed her, and she's been working there ever since, where she's head of analytics there. So this was one of the early success kind of blog conference stories of getting into football analytics. Just to give some more details of what she did. So she broke the pitch down into 7 areas. The 0 area here, this is the kind of not worth very much area. This is the 2 area here in front of the box. This is the outer corridors. So you have further out and further in, and then on the left and the right hand side, and then you have in the box. And then she made a transition matrix, which looks at the probability that you go between these different areas. So this would be the end of possession. This is scoring a goal. And then these are the transition probabilities. The probability you go from 6 to 5, from 6 to 3, and so on for this model. And she estimated those using Opta data to parameterize the model. I'm going to go into a little bit more detail about another method where we do something similar. And from that, she could say, well, she could evaluate players, because once you've got a model of the probability of doing transitions to different areas, and you start to know the probability of the final transition being a goal for those things, then you can actually see how much players are contributing. So if a player 1 starts in an area where the probability of a goal is 0.25, and then she does an action which reduces the probability of a goal down to 0.17, then we give her a negative score. But if player 2 then gets the ball and does a action which increases the probability of scoring from 0.17 to 0.28, so that might be, for example, a move from here into the box, then we give her a positive score. And then if the player 3 takes the ball from that area and actually scores, then she gets the difference between the probability of her scoring before she got the pass to that area and the fact that she scored a goal, because once you scored a goal, probability of scoring a goal is 1. Good. So that's a very nice model. I'm sure Arsenal aren't still using exactly that model. They'll have moved on since then. But in the public domain, Karan Singh has done a very nice model, which is basically the same, but breaks the pitch down into a somewhat finer granularity. I think I want to, I'll just go through this first, then we'll go into Karan's webpage and we will have a look at that. So here we have Premier League average. So on average, when a player has the ball here, 70% of the times he will move the ball to somewhere else, pass the ball to somewhere else. 30% of the time he'll shoot with a 2% chance of scoring. You can go in, we will go in and have a look at this, and you can hover and find out how this changes in different parts of the pitch. But this is what he's worked out in advance. What's the probability that in particular places on the pitch you move or you shoot? Then you can formulate, so that this thing we've calculated here, these are actually the transitions to the different states. And so he formulates the model as follows. There's a bit of maths here, but I think I should be able to explain what the bits do. So you start off with VXY. So VXY is the value that our algorithm assigns to a zone XY. So these are the zones XY, got X coordinates here, Y coordinates there. What we want to do is assign a value to every zone, and that's going to be represented by VXY. Before we start the process, we don't know VXY. It's the hardest thing for us to know in this algorithm. But what we do know is GXY, because based on past data, we know that whenever you shoot from a particular thing, you score with a certain probability. Well, GXY, that is expected goals, right? Because if you shoot from position XY, you have a probability of scoring G, then that is the expected goals of that position XY, not accounting for any other factors in this case. And SXY is the probability that a player decides to shoot from that particular point. And here, for example, SXY would be 0.3, and MFXY is 0.7. It's 1 minus SXY. It's the probability you move the ball to a different place. I'm going to put all of these up so you know. So value is what we're going to calculate. We've got the value for a particular point XY. This is the probability of shooting. This is the probability. This is the expected goal probability of scoring. This is the probability you move the ball. Now you multiply this by the transition probability from moving the ball from position XY to another position, ZW. And so this is when you decide to move the ball, and you might dribble or you might pass. But this is the probability, and this is the one that Sarah Rudd worked out in her study as well. It's a probability that you transition from this point to another. And then VZW is then the value of that particular new place that you've moved in. So you've got the value of the old place and the value of the new place that you've moved to. So just to give an idea, okay, so this gives you an equation. Basically, if you can solve this equation, you know everything here. You know the shoot probability from data, you know the expected goals, you can work out the move probability, you can work out the transition by finding out how often you move to different places. The only thing you don't know is the value of the different things. And you can solve for the value in the following way. what you do is you start by assuming that the value of every point on the pitch is 0. Okay, so we just have a flat thing. What I haven't said here is that this vxy has been replaced, the v has been replaced with a thing called xt. So v and xt have the same, they're just basically the same thing. He wanted a nice, instead of value, he wanted to have some nice name for it, so he called it expected threat, and that's what xt means. So the v is replaced by an xt. And so you start off with xt equal to 0 in this equation, and then you'll put 0 on the right-hand side of this equation, put it 0 in here, and everything here becomes 0, this all becomes 0, and you're left with the update for vxy is basically the shot probability times the expected goal. So you do an iteration where you find out on the next time step, the expected threat is the shot probability times the expected goal probability. That's nice. And then you do another iteration. So now you've got a new estimate for xtxy. You do another iteration, and now you use the full equation. So here will be everything that you've used for here will be your expected goal. And you update this thing and it sort of moves out. So if you look at the heat map here, it moves out away from the box. There's a lot of value down here now, which wasn't value for shooting. There was no reason you should shoot from there. But now on a second step, one step away from the goal, this has a reasonable value. Like Sarah, he's an Arsenal fan. I don't know if he was inspired by watching Arsenal to also come up with a similar idea here. But here's the clickable map. So this is the transition probabilities between the different places. You can go in and click on it. Here's the argument that I've been through, how it's evolved. And then in the end, of course, Kevin De Bruyne always comes out top of every statistic you ever do on these types of things. But in the end, you can find out where different teams do create danger. So you can fit these things individually for different teams. So from this particular point, the top contributors who create the most danger are Kevin De Bruyne, Bernardo Silva, and Kyle Walker. And they do so by passes to the red areas. So if you have the ball there, the ball typically is moved or passed or dribbled to the red areas next. And that's where you create danger. This is what Manchester City, that particular season, were uniquely good at, was getting the ball back to down to the line and then getting the ball in to shooting positions from the line. And you can actually see this quite clearly here. I think this is a lovely tool for analyzing how different teams generate danger, where the ball is likely to come to next. You'll see also, when you look at this in more detail, you see that it's almost always better to play the ball centrally than it is to play out to the edges. So you get more danger if you come in centrally than you do playing out. So that's always, I think this is one of the ways in which football analytics has changed a bit the way that football is played, is that this emphasis on playing central instead of getting the ball out to the wings and trying to come in back from there. Okay, so that's where it's dangerous. Yes, limitations. You have to know the correct time and spatial scale, right? So that, I think that's the biggest limitation of this approach, is that why do you break into a particular number of boxes? And in fact, although Karan does it on a lower resolution scale, I'm not sure that the original scale used by Sarah was not the best scale to do this on, just to define different areas of the pitch and use that in order to work it out. It's very difficult to know exactly what scale you should use. That's basically trial and error. You can't use a tiny scale. You can't use too big a scale. You probably do want to use something between, I would, if I was going to do this, I would not just use Karan's grid. I would use something that's makes more footballing sense. So for example, you have 5 lanes. You often talk about 5 lanes, or you can maybe talk about 7 lanes, and certain areas have more value in the X direction than others. So you would have less value much further along the pitch, back along the pitch, and you would have a more granularity further to the right on the pitch. So something like that. But I think the main restriction, so unfortunately, this is one of these things where I'm going to tell you something which I just know from personal experience rather than I've published anything which can tell you this, is that the biggest problem with this approach is if you simulate the movement model, how the ball moves around the pitch, you never get any goals. So it tends to be the case that you just don't get a realistic simulation of football using the approach that that they use. So it's a valuable starting point, but it doesn't tend to give you a realistic simulation of football. Maybe I should elaborate on that slightly. What I mean by simulation is that, so say you just start with a ball at some random XY, you use the transition matrix to move the ball around. What you'll find is that the ball will hardly ever go near to the goal. It just sort of pops around in a very conservative way. And this is because it doesn't capture the memory process of football. There is these sort of sudden attacks and sudden movements which aren't the average, they're unusual. And that's what makes a good attack in football. And that isn't captured by this particular model. So the simulations of this tend not to be particularly realistic, I think, or I'm reasonably sure. But they do start to break down the values of different areas of the pitch. So I think it's a starting point, but it shouldn't be the end point for where we're going with this.